You drew a gold coin. It may seem like there is a 50-50 chance that the other coin is also gold, but the exact answer is 2/3. First, there is no need to be intimidated. All the math we need is multiplication, division, and a few fractions. And yet, this one simple calculation has tripped up countless people for 137 years. Our story begins in Paris in 1889. The French mathematician Joseph Bertrand published a probability textbook called Calculus of Probabilities. Near the beginning of the book, he planted a small trap. It was like a vaccine against a common mistake in counting probabilities. The version commonly told today features 3 boxes that look exactly alike. The boxes contain gold gold, gold silver, and silver silver. With your eyes closed, you choose one box at random with each box equally likely. Without looking inside, you draw just one coin. You open your hand. The coin you drew is gold. What is the probability that the other coin in that same box is also gold? The problem itself could hardly be simpler. The only catch is that the answer clashes with almost everyone's first instinct. No complicated code is needed. With just pictures and careful counting, we can follow every step where our intuition loses its footing. Before we analyze it properly, choose your answer in your head. You need to commit to an answer now so you can really feel the collision between intuition and truth in a moment. You chose one of the gold gold, gold silver, and silver silver boxes at random, and the coin you drew was gold. Our first instinct immediately rules out the silver silver box. Since we saw a gold coin, that part is completely correct. Exactly 2 candidates remain: gold gold and gold silver. There are 2 candidates, so it must be 50-50. That is the neat answer many people give first. But the correct answer is 2/3. There are exactly twice as many cases in which the other coin is gold as cases in which it is silver. If your reaction is, "That can't be right," that is perfectly normal. Bertrand designed the trap to provoke exactly that response. Now let us defend the 50-50 intuition, then find the exact point where it slips. Our reflex to say 50-50 even has a name. Cognitive psychologists call it equal probability bias. When information is scarce, the brain assigns equal probabilities to the options that remain. It is a quick rule of thumb that reduces mental effort. It is correct that the silver silver box is eliminated, leaving only gold gold and gold silver. The reasoning fails at the final step. It treats the 2 survivors as equally likely simply because there are 2 of them. Tomorrow a meteor either hits our neighborhood or it does not. There are 2 outcomes, but their probabilities are not 50-50. The fact that 2 candidates remain is completely different from the claim that those 2 candidates are equally likely. So we need to ask one more question. Which candidate is better at producing the evidence we just saw? The evidence in front of us is one gold coin in the palm of our hand. The gold gold box contains 2 gold coins. The gold silver box contains only 1 gold coin. Just one path, the one that reaches that coin, produces our evidence. Even though the observed coin is gold either way, the gold gold box produces that result twice as readily. After seeing gold, the 2 candidates carry weights in a ratio of 2-to-1. Therefore, gold gold has probability 2/3 and gold silver has probability 1/3. Our intuition missed the number of paths. So far we have assumed fair random choices. Each box has probability 1/3. And each of the 2 coins inside a box has probability 1/2. If the phrase "twice as likely" still feels suspicious, we can lay out every outcome and count them directly. Let us name all 6 coins. The gold gold box has gold 1 and gold 2. The gold silver box has gold 3 and silver 1. And the silver silver box has silver 2 and silver 3. Choosing a box and then 1 coin from it ultimately means that one of these 6 coins lands in your hand. 1/3 times 1/2 equals 1/6. Every coin is equally likely to land in your hand. Now apply the evidence that the coin is gold. Of the 6 paths, only gold 1, gold 2, and gold 3 remain. Each of the 3 surviving paths originally had probability 1/6. Even after conditioning on gold, they remain equally likely relative to one another. If you are holding gold 1 or gold 2, the other coin is also gold. If you are holding gold 3, the other coin is silver. 2 of the 3 equally weighted paths end with the other coin being gold. That is why the answer is 2/3. The 6 bars on the left are all the same height at 1/6. For 2 of the 3 yellow bars, the other coin is also gold. In the bar chart, the silver box's 1/3 share appears to flow into gold. The actual calculation conditions on gold and renormalizes the probabilities. In conditional probability form, divide the share of gold outcomes produced by gold by the overall probability of gold. 1/3 divided by 1/2 is 2/3. The denominator, 1/2, is the overall probability of drawing one of the 3 gold coins among the 6 coins. The same calculation gives gold-silver 1/3 and silver-silver 0. Originally, each box had 2 drawers with 1 metal in each drawer. Then one drawer was opened at random. He asked about the box, not the remaining metal. After seeing a gold metal, what is the probability that the chosen box is the gold-silver box? Before the draw, the mixed box has probability 1/3. But the 50-50 argument says that after seeing gold, 2 candidates remain, so its probability must be 1/2. Then we must use the same argument after seeing a silver metal. Eliminate the gold box, leaving silver and gold-silver, and once again we get 1/2. If the answer is 1/2 regardless of the observation, it should already have been 1/2 before opening the box. But it started at 1/3, so the 50-50 argument contradicts itself. The correct answer is that the mixed box remains at 1/3 even after seeing a gold metal. Silver falls to 0, while only gold rises to 2/3. The probability of a gold metal from the mixed box is 1/2. The overall probability of a gold metal is also exactly 1/2. Bertrand's warning is simple. When candidates are eliminated, do not redistribute the probability equally by simply counting the survivors. When the arithmetic is right but your intuition still resists, probability has a final judge. Repeat the trial a great many times. As the number of trials grows, the observed proportion approaches the true value. This is the law of large numbers. Instead of physical boxes, a computer repeats the random experiment 300,000 times. This kind of repeated experiment is called a Monte Carlo simulation. We discard every trial in which the first coin is silver. The question itself begins with the condition that we drew gold. Among the remaining gold trials, we count how often the second coin was also gold. Intuition predicts 50%. The correct calculation predicts about 67%. The results split just as this chart shows. As trials accumulate, gold settles near 2/3 and gold-silver near 1/3. In this run with seed 1889, there were 150,090 gold trials. We discarded the 149,910 silver trials. In the same run, the gold share was 66.51%, and the gold-silver share was 33.49%. A hands-on experiment uses the same procedure. Discard the silver trials and count only the gold trials. The proportion with a silver coin left is exactly the proportion that came from the mixed box. Now let us disturb one quiet assumption: that the 2 coins inside a box are truly drawn with equal probability. Imagine that the gold coin in the mixed box is larger and heavier, making it easier to grab first. Then the very same observation of gold can lead to a different answer. Let P be the probability of drawing the gold coin first from the mixed box. When P is 0.5, the draw is fair. When P is 1, gold is always drawn first. Both probabilities have 1 plus P in the denominator. The numerator is 1 for gold and P for gold-silver. The midpoint of the graph is the fair world we have considered so far. When P is 0.5, gold is 2/3 and gold-silver is 1/3. When P is 0.25, the gold to gold-silver split is 80-20. When P is 0.75, it is 57.1 to 42.9. As P increases, the mixed box also produces gold more easily. So seeing gold becomes weaker evidence for the gold box. With box selection still fair, as it is here, the 2 curves meet at 50% when P equals 1. Only then is the answer 50-50. No one promised us that drawing rule. Intuition did not merely fail to calculate. It quietly imported the answer from a different world. At the other extreme, when P is 0, the mixed box always produces silver first. If we see gold in that world, the gold box has probability 100%. Probabilities are shaped not only by the fact that gold appeared. The crucial question is what procedure produced that gold coin. There are 3 fairness assumptions: how we choose the box, how we choose within the mixed box, and how we choose within a box whose 2 metals match. The third assumption does not affect the answer. Either coin from gold is gold, and either coin from silver is silver. Let B1 and B2 be the probabilities of choosing the gold and gold-silver boxes, respectively. Let P be the probability of drawing gold first from the mixed box. The denominator is B1 plus B2 times P, and the numerator is B1. The silver box does not appear in the denominator at all. It has no path to producing gold, so it cannot enter the world in which we observed gold. Put 1/3 plus 1/6 in the denominator and 1/3 in the numerator. The result is 2/3. 2/3 is not a constant decreed by nature. It rests on the promise that we choose both the box and the coin fairly. Now that we have opened all 3 boxes, let us take our tools with us. Only 2 methods were needed to defeat intuition. First, do not count cases. Count the paths to the evidence. Gold has 2 paths and gold-silver has 1, giving a ratio of 2 to 1. Second, if the value would be the same no matter what news you received, it should not have moved in the first place. The claim that both gold and silver lead to 50-50 collapses. The calculation that updates an old probability using new evidence is Bayes' theorem. Multiply the prior probability by the likelihood, then normalize by the total. Spam filters and diagnostic tests use the same calculation, especially when a disease is rare. A substantial share of positive results may be false positives. The same structure led to larger puzzles: the 3 prisoners problem in 1959, and the Monty Hall problem in 1990. In 1990, Marilyn Vos Savant's column brought the Monty Hall problem, with 3 doors, 1 car, and 2 goats, to the wider world. The gold coin corresponds to the guard statement, and the goat door opened by the host. The mixed box corresponds to the prisoner asking the question and the initially chosen door. The Monty Hall problem caused a worldwide sensation in 1990, but the blueprint for its trap had already appeared in a Paris textbook 101 years earlier. Just like the box's drawing bias P, the host's door selection rule changes the answer in the Monty Hall problem. The procedure determines the weight of the evidence. Bertrand's paradox, without the word box, is the random chord problem in a circle. Its answer can take 3 different values depending on how randomness is defined. Whenever something seems to have only 2 possibilities, ask this before dividing the probability: are those 2 possibilities really equally good at producing the evidence we have? A late friend's text could be caused by traffic or by oversleeping. Which explanation is more likely to produce that message? Bertrand's box waited 137 years to teach us that one question. It is the smallest and oldest probability classroom in the world. If you enjoyed today's video, please subscribe, like, and turn on notifications. See you again in the next story.